All right, we've been talking about circular motion and centripetal acceleration, centripetal force. And one of the types of circular motion that has been observed throughout history is a circular motion that seems to occur from the motion of planets and the motion of stars and just observing the sky. So I want to give you a little bit of a historical perspective to see how we got to where we are now with our understanding. Now, this is not a history class, so I don't expect you to remember names or dates or things. I expect you to remember some of the ideas that were presented and thought through. So the first of these ideas that we want to talk about is the idea of our universe, the model that we have of the universe. And the first person to get some credit for that is Ptolemy. He's a Greek philosopher and astronomer in the AD 100 period, so over 2,000 years ago. And he came up with the geocentric theory, the idea that Earth was the center of the universe. And if you look at the sky and you look at the stars and planets over a period of time, you could see that they progressed around our perspective. And so it's a natural perspective to look at and see that these things in the sky are moving. The planets were observed to move faster than the stars. So the planets were really the focus of the observers in early astronomy type times. And they were named planets because planet means wanderer, and they seem to move faster and have a pattern that was more recognizable than the stars. And so different astronomers thought of different things throughout the years, but the geocentric theory was the focus that they had, which was that the Earth, geo means Earth, was the center of the universe and everything revolved around the Earth. That was a prevalent theory until later in time, and you can see about it took over 1,500 years until Copernicus came around, and Copernicus came up with what is known as the heliocentric theory. Now, obviously, these two were not individuals that were the only people to think about this, but they were the ones that publicized it and really pushed these ideas. Now, Copernicus was persecuted by the church because the geocentric theory seemed to fit the model that if we're created by an almighty creator and we're unique in the universe, that why wouldn't he put us in the center of the universe? So there was a lot of fight from the church, and because the church was the main educational basis for people, so it took a long time for Copernicus's ideas to come and be really made known. Both of these models work. Now, we know that neither the Earth or the Sun are the center of the whole universe, but when we talk about the solar system, um, we look at it as a model of heliocentricity. All right. We can see a difference in these two, and Copernicus's idea was that the geocentrism gave us a much more complex situation than heliocentrism. And so we didn't have a good mathematical, easy, predictable model. Copernicus had the idea that this perfect shape was a circle or a sphere. And so when he came up with this idea, he said, well, things must be moving in circles. So if I look at the motion of a planet compared to the Earth, sometimes it goes one direction, sometimes it retrogrades and goes in the opposite direction. So there's something wrong there. But if I look at it from the perspective of the sun, it seems to go around in a full circle all the time. Now, there are some problems with Copernicus's ideas because he thought the perfect shape was a circle, and that we found out was not quite the case. But that was the prevailing thought, and that has been the prevailing thought since then. Neither model is incorrect, but this is an easier mathematical model, a heliocentric theory. Then along comes a guy who is my favorite guy in all of science, Tycho Brahe. First of all, he has a cool name. He was kind of the Kanye of his time. Tycho was a very rich guy. He was a mathematician and astronomer. And really, his contributions to physics aren't as big as the people who came after him, but he's fascinating. All right. Tycho was the royal astronomer for Denmark. He was kind of a rich playboy type of guy. Uh, and this guy lived quite a life. As you can see, he has quite a beard. You know, he's kind of my uh, beard hero with that mustache there. So I have a long way to go to get to Tycho level, but I'm working towards it. Um, but he lived in, as you can see, the late 1500s, and his really biggest contribution is the records that he kept, and he was very meticulous about keeping the records. But he was a man that had quite a life. Um, First of all, he was a man that had a lot of temper. And one point in his life, he actually got his nose cut off in a duel because he got in an argument about mathematics with someone, and challenged him to a duel and got his nose cut off. So he had a metal nose crafted by someone. So the guy had kind of an ego. He couldn't go around without a nose, so he had a metal nose and had it sculpted and wore that. Probably had multiple noses, you know, a good nose for parties and stuff because he was a partier. He he had a large estate, castle type place. The man threw a lot of parties. Get this, he had a pet moose. Who has a pet moose? All right. I could see Kanye having a pet moose at some point in time. But Tycho had a pet moose, and the moose was allowed to roam the grounds and party along with people. And the problem is that the moose drank too much, and at one of the parties, it got drunk and fell down the stairs and was killed. So this is the 1500s. This is legendary type stuff. Tycho is amazing. You don't need to know anything about Tycho in physics, but he's fascinating. The way he died, also fascinating. Apparently, he was at a royal banquet, and because he hung out with royal people and went to all these parties and could drink a lot and eat a lot. And he drank so much that at one point, apparently, etiquette forced you not to excuse yourself to go to the restroom until the host did. He held it in and his bladder burst. And he died 11 days later because he was all infected. That's amazing. All right. That's not how I would want to go, but the guy lived an amazing life. Um, Now, we know this kind of stuff because his protege was Johannes Kepler, and Johannes Kepler has a much greater contribution to physics and our understanding of gravitation. But some people think Kepler might have, been in on a plot in killing Brahe. But Brahe had all these mathematical records and didn't have a great understanding of how to use them. In fact, if you look at this slide here, this is Brahe's model of the universe. It's kind of a geocentric, heliocentric type of mishmash. It has the sun and moon orbiting the Earth and everything else orbiting the sun. So he didn't really get it. It was kind of weird in how he modeled stuff. But his protege, Kepler, who worked with him, was able to look at all these different data points and observations that Brahe had made over the years and kept, and was able to come up with the three laws of planetary motion, which are still valid today. And we use these laws to understand how we can send satellites out and different things. So those of you that took AP Euro, you probably have heard of all of these guys, Brahe and Kepler. Brahe's the stud, and I would love to name a dog Tycho Brahe. I think it's a great name, but my current dog's name is Kaya, and my former dog's name was Abby, so you can tell that I don't get to name the dogs in the family. All right. Uh, anyway, Kepler's three laws of planetary motion is what I want to talk about today. So Johannes Kepler came up with these laws of planetary motion, and what he did was change the ideas that Copernicus had a little bit. Copernicus thought the perfect shape was a circle. Well, it's not. It's an ellipse in terms of orbit. So Kepler came up with the idea that the elliptical orbit, or a near circular ellipse, is how orbits worked. So when things were orbiting the sun, they were going in nearly a circle, but not quite, a little bit elliptical. So he really focused on the planets around the sun. We now have expanded his ideas to anything that orbits, but he was really looking at the solar system. So the first law of Kepler's law is that all orbits are nearly circular ellipses. The circle is not the focus of that, but they're nearly circular. His second law is kind of a relationship between the distance that something is away from the planet or from when it's orbiting and how fast it goes. So I have this app up on my computer, and this is a model of different planets. So this is Mercury orbiting the sun, and Mercury orbits the sun in a ellipse. The number that's eccentricity tells you how elliptical it is. The closer that number is to zero, the closer to a circle it is. That means the sun is right in the center. So you can see that at certain points, Mercury is closer to the sun than it is at other points. Every planet has this situation, all right? So what Kepler figured out, and I don't know exactly how he figured it out, but was that the planet travels a certain distance and it moves faster when it's closer to the sun. So the area of a sector, and here's a sector, for example, let me put a sector in this. The area of a sector would be kind of a pie piece. There's a sector. The area of that sector, that pie piece, is the same for the same period of time. All right, so that means if, for example, this is 10 days worth of Mercury's orbit. For 10 days worth of Mercury's orbit over here on the right-hand side, it travels much farther than it does down here on the bottom. But the area of this red wedge and the area of this red wedge are equal. You can kind of think of them as areas of triangles, even though one side is not quite straight. So 1/2 base times height, the closer it is to the planet or to the sun, the shorter the height, but the wider the base. All right. So when it's really far away from the sun, like right here, we get a narrower base than any other place. So we see that on different situations. We can look at different things. When we get a really odd eccentric orbit, like Halley's Comet, which shows up once every 76 years, when it's really far away, it's moving really slowly. And we can see that here, that it doesn't move very fast. In fact, I can speed this up a little bit, and it really doesn't move very fast at all. But when it's really far away, it just takes a little bit of portion of that. As it approaches, it speeds up and speeds up and speeds up. And when we get really close, then it whips around. So that area of red is the same area, but it goes a lot farther distance in the same time when it's close. All right, so Kepler thought the distance that a planet is from the sun is what determines how fast it moves. So there's a relationship there. Now that's in a single planet. Now, in comparison of planets, he also said, well, the closer a planet is to the sun, the faster it should be moving, so less time it takes to go around the sun. So a year on Mercury, which is closer to the sun than Earth, is less than a year on Earth. But a year on Jupiter, which is farther away from the sun than Earth, is more than a year. And he was able to figure out that the average distance from the sun and that period, which is the time it takes to happen once, are related. Now, I have no idea how he came up with this relationship, but it kind of goes with the second law that the closer a planet is to the sun, the faster it's moving for its own orbit. But when we have planets that are closer, they're moving faster than planets that are farther away. So you can see it in words here. The ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. This is the only one of Kepler's laws that is mathematical. And here's our formula. So period A over period B. So if you compare the year of one planet to the year of another planet and square them, it's going to be the same ratio as the radius of one planet's orbit over the radius of the other planet's orbit cubed. He must have done so many calculations to figure that out. I don't know how, I can't imagine in the 1600s how that was figured out. But Kepler came up with this idea. That means, and you'll see this in a few different ways, but usually what we'll do is compare the orbits of two planets or the years of two planets, the periods of two planets. And we'll get that figured out. So basically what it's saying is the closer the planet is to what it's orbiting, the faster it's got to move and the less time it takes to go around. But there's a relationship, and that relationship is predictable based on this relationship. So we can answer a question like this. If we know how long the period of Mercury is, the year on Mercury is 88 days, how far is Mercury away from the sun? Now we know Earth is 15 billion miles away from or meters away from the sun. So we want to know how far Mercury is away from the sun. So we can look at that in terms of, actually it's 150 billion, I should say. We can look at that in terms of that. We can also look at it in terms of proportion. So sometimes you might see if something takes 3 times farther to go around, how much farther is it? And then we just put a ratio on this formula. We could say, well, TA over TB is 3. 3 squared equals whatever cubed, and solve for the ratio of radii. So sometimes you'll see that. But if we take these numbers here, we can figure out, here's our question, here's our data. We know the period of Earth, we know the period of Mercury, and we can solve for how far away Mercury is away from the sun. And 5.79 times 10 to the 10 meters versus the Earth is 1.49 times 10 to the 11 meters. So it is significantly farther away, about 3 times farther away Earth is from the sun than Mercury. So when we compare planets, when you see a question that compares the orbit of planets, the radius of planets, or the period of planets, this is what you're going to use. All right. You guys have a great week, and I will talk to you later. Thank you.